Hi there, and thanks for tuning in. Today we're going to talk about Pythagorean triples. We will enrich students' understanding of Pythagorean triples through deriving a formula to find these. Students learning the Pythagorean theorem at the secondary level may recognize certain common ordered sets of three numbers that can represent the lengths of the sides of a right triangle. Some of these sets of three numbers, known as Pythagorean triples, are the following: 3, 4, 5, 5, 12, 13, 8, 15, and 17, 7, 24, and 25. We can see that in all cases, A, B, and C are positive integers. Each set also contains a prime number, making these all primitive Pythagorean triples. If we are asked to find the missing members of the following Pythagorean triples, we can easily determine the first two simply by using the Pythagorean theorem. However, this method does not work with the third triple. We can look at a method for solving this problem, but before we develop the desired formulas, we must consider a few simple lemmas. Lemma 1. When 8 divides the square of an odd number, the remainder is 1. For proof of this lemma, we can represent an odd number by 2k plus 1, where k is an integer. 2k plus 1 squared equals 4k squared plus 4k plus 1. Factoring this, it reduces to 4k times k plus 1 plus 1. Since k and k plus 1 are consecutive, one of them must be even. Therefore, 4k times k plus 1 must be divisible by 8. Thus, 2k plus 1 squared, when divided by 8, leaves a remainder of 1. Lemma 2 follows as a direct result of this proof. When 8 divides the sum of two odd square numbers, the remainder is 2. Lemma 3. The sum of two odd square numbers cannot be a square. For proof of this lemma, we can see since the sum of two odd square numbers, when divided by 8, leaves a remainder of 2. The sum is even, but not divisible by 4. It therefore cannot be a square number. We can now begin our development of the formula for Pythagorean triples. Let us assume that A, B, C is a primitive Pythagorean triple. This implies that A and B are relatively prime. Therefore, they cannot both be even. Can they both be odd? Well, if A and B are both odd, then by lemma 3, a squared plus b squared cannot equal c squared. This contradicts our assumption that A, B, C is a Pythagorean triple. Therefore, A and B cannot both be odd. Therefore, one must be odd and the other must be even. Let us suppose that A is odd and B is even. This implies that C is also odd. We can then rewrite a squared plus b squared equals c squared as b squared equals c squared minus a squared, or b squared equals c plus a times c minus a. Since the sum and the difference of two odd numbers is even, we know c plus a equals 2p and c minus a equals 2q, where p and q are natural numbers. We can now show that p and q must be relatively prime. Suppose p and q were not relatively prime. Say g greater than 1 was a common factor. Then g would also be a common factor of a and c. Likewise, g would also be a common factor of c plus a and c minus a. This would make g squared a factor of b squared, since b squared equals c plus a times c minus a. It follows that g would then have to be a factor of b. Now if g is a common factor of b, and also a common factor of a and c, then A, B, and C are not relatively prime. This contradicts our assumption that A, B, C is a primitive Pythagorean triple. Thus P and Q must be relatively prime. Since B is even, we may represent B as B equals 2R. But B squared equals C plus A times C minus A. Therefore, B squared equals 2P times 2Q, which is equal to 4R squared. Simplifying this, PQ equals R squared. If the product of two relatively prime natural numbers, P and Q, is the square of a natural number R, then each of them must be the square of a natural number. Therefore, we let P equal M squared and Q equal N squared, where M and N are natural numbers. Since they are common factors of relatively prime numbers, P and Q, they, M and N, are also relatively prime. Since A equals P minus Q and C equals P plus Q, then A equals M squared minus N squared, and C equals M squared plus N squared. Also, since B equals 2R and B squared equals 4R squared, B squared equals to 4PQ. We then know that B squared equals 4 times N squared times N squared, which reduces to B equals 2 times N Mn. We now have formulas for generating Pythagorean triples, where A equals M squared minus N squared, B equals 2mn, and C equals M squared plus N squared. The numbers M and N cannot both be even, since we have established they are both relatively prime. Likewise, they cannot both be odd, for this would make C equal M squared plus N squared an even number, which we established earlier as impossible. Since this indicates one must be even and the other odd, as B equals 2mn must be divisible by 4. Therefore, no Pythagorean triples can be composed of 3 prime numbers. This does not mean that other members of the Pythagorean triple may not be prime. Let us reverse the process for a moment. Consider relatively prime numbers m and n, where m is greater than n, and where one is even and the other odd. We will now show that ABC is a primitive Pythagorean triple, where A equals m squared minus n squared, B equals 2mn, and C equals m squared plus n squared. It is now simple to verify algebraically that m squared minus n squared plus 2mn squared equals m squared plus n squared all squared. This confirms our formula for Pythagorean triples. What remains is to prove that A, B, and C is a primitive Pythagorean triple. Suppose A and B have a common factor, h greater than 1. Since A is odd, h must also be odd, because a squared plus b squared equals c squared. H would also be a factor of c squared. We also have h a factor of m squared minus n squared and m squared plus n squared, as well as their sum, 2m squared, and their difference, 2n squared. Since h is odd, it is a common factor of m squared and n squared. However, m and n, and as a result, m squared and n squared, are relatively prime. Having finally established a method For generating primitive Pythagorean triples, students should be eager to put it into use. The following table gives some of the smaller primitive Pythagorean triples. They should notice that for these triples, m equals n plus 1. To prove this will be true for other primitive Pythagorean triples not included in the table. Let m equal n plus 1 and generate Pythagorean triples. A equals m squared minus n squared. Substituting n plus 1 for m, we can see n plus 1 squared minus n squared equals 2n plus 1. B equals 2mn. Substituting n plus 1 in for m, we can see 2n times n plus 1 equals 2n squared plus 2n. C equals m squared plus n squared, which is equal to n plus 1 squared plus n squared, which is equal to 2n squared plus n, or plus 2n plus 1. Clearly, C equals b plus 1, which was to be shown. Another question to ask your students is to find all Pythagorean triples that are consecutive natural numbers, in a method similar to the one shown above. They should find that the only triple satisfying this condition is where a equals 3, b equals 4, and c equals 5. Other potential investigations students can pursue are: find a way to generate primitive Pythagorean triples of the form a, b, c, where b equals a plus 1. Prove that every primitive Pythagorean triple has one member that is divisible by 3. Prove that every primitive Pythagorean triple has one member that is divisible by 5. And finally, have students prove that for every primitive Pythagorean triple, the product of its members is a multiple of 60. Thanks a bunch for tuning in today. Have a good day.